All right, so this lecture is going to be about surface tension. All right, surface tension is a property of fluids, and it matters in both fluid mechanics and dynamics and fluid statics, but we're mainly going to focus on fluid statics. And so the first thing to understand is what is surface tension. So the idea of surface tension, and sometimes we'll also use the term interfacial tension, I'll explain the difference, is that we have a surface. And let's say we're going to call this liquid A. All right, and above it, we're going to have liquid B or air. So the first thing is that surface tension is when we have liquid A and air, and interfacial tension is when we have liquid A and liquid B. Okay? And essentially what we have here is, I'm going to draw some molecules. So we have, I'm just going to call these pluses, all right? And so liquid A is plus molecules, and they're sort of all over the place, like this. I'm just going to draw them in randomly. We'll say that liquid B or air, we'll just make them minuses. It's not really that they're charged here, it's just so that we can distinguish them by shape. Okay, so when we think about a liquid interface, we typically tend to think that it has this really distinct line like I've drawn here. But realistically, that's not the case. What happens at that interface is we have a couple of molecules here, and maybe one even gets up here. And then we have some of these red guys, one's down here, all right, maybe to here and to here, all right. And so there's this region where there's mixing of the two kinds of liquids. So there's this mixing region. Now here's the thing about what's going on here. In this region where there's this mixing, what we would sort of call the interface region, and the reason we think about it being a sharp line is because far away, this region might be, 10 atoms thick. So for all intents and purposes, it's a sharp line. But what's happening is, in this region, things are mixing. And the thing about mixing is, for most fluids, they don't like that, especially if a fluid has a high energy of attachment. So for instance, if the liquid A was water, we know that water molecules really love, ideally, what a water molecule would like is to be surrounded by other water molecules, right? And if liquid A was an oil or something, ideally, right, this is what it would like. In both cases, this molecule in the middle is really happy because it's completely surrounded by other molecules of its type, and that's what makes it happy. But in our mixed region, right, where we have this, all right, we have in this mixing region, the molecule here, let's just take this guy here, right, he's surrounded somewhat by his own, pluses, and somewhat by minuses, and that's not good. Energetically, this guy is unhappy because he's not surrounded by all pluses, all right? And so what happens so what's going on is at an interface, it is energetically unfavorable. And what I mean by that is this idea that molecules at the interface are in a position where they're surrounded by not molecules of their own type, and that is energetically unfavorable. Now we know one thing about the world and thermodynamics, remember, right? Everything wants to be in its lowest energy state. So if I take this fellow at the interface, let's call him 1, and I take this guy 2, if I think about the energy of 1 versus the energy of 2, 1 has a greater energy than 2, all right? And so that's an energetically unfavorable situation. So any molecule at the interface is in an energetically unfavorable situation. All right, and that means, in general, fluids want, and I say want, it's not like it actually wants, but fluids want to reduce their interfacial area. Okay? because it's energetically unfavorable. What that also means is that in order to get a molecule to the interface, I have to add energy to it. So to go from 1 to 2, I have to add energy. Okay? Now, this idea of energy is really important, and that's really what surface tension is, okay? Realistically, when we talk about surface tension, we have a property of the fluid which we call surface tension. Usually it's gamma. Sometimes you'll see it as sigma, but it doesn't matter, all right? We'll use gamma right now. Okay, and this surface tension value is a property of the fluid, two fluids, or the air and the fluid and the gas that it's touching. All right, and it's really got units. It's really this energy, really, of the energy per unit area. All right, which, if we remember, that's joules per meter squared. And really what we're talking about here is the amount of energy it takes to move molecules such that they create an area of interface, and how much energy it takes to move each molecule. So for every amount of area where I create interface, I've had to move more molecules to the interface, and that required energy. Now the thing is, if we look at the units of joules per meter squared, okay, if you remember that that is equivalent to newtons per meter over meters squared, because a joule is a newton meter, which means that this is equivalent to a newton per meter. So one way to think about surface tension is an energy per unit area, but because of units, we can also think about it as a force per the perimeter of the area. All right? And so if we call this the area of the interface, this would be the perimeter of the interface. And I'll talk about what that means a little bit more in a second. All right, so really, this top idea in blue, this is really what's happening, okay? But in red, this is often, as mechanical engineers, what we end up talking about. Right. So there are two important things. One, that surface tension can be thought of as an energy per unit area, and two, of the interface. And two, that surface tension can be thought of as a force per unit perimeter of the interface. And I'll talk again about what that means more. All right. So this is a force per unit length or an energy per unit area. All right. So there's some really important consequences of this. All right. The first consequence is one, it costs energy to create interface. Okay. And two, if we attempt to deform an interface, right, a force results. Okay, so a quick example. All right, now normally we'll do examples in class, but again, just a quick example of these two consequences. All right, let's pretend we have a wall that looks like this. All right, and at the bottom of this wall, there's a plate. All right, and there's a hole in this wall, and above this wall, there's lots of fluid, so the fluid can flow in through this hole. All right, and this fluid forms a bridge between the wall and the plate with a radius of r. Okay, and it's in equilibrium. All right, so what's holding up the plate? So this plate might have a mass m. All right, what's holding up the plate? All right, surface tension. All right, so where is the surface tension force? First, we have to figure out, remember that the surface force of surface tension is equal to the surface tension value sigma times a perimeter of the wetted contact line. What's the wetted contact line? Well, looking at my picture here, if I do a top-down view, and I think about this plate here, right, there's this blue cylinder of fluid, right? So this is my top view. All right? And so if I think about this cylinder, then this line here, which I'm just going to dot in red, this is the wetted contact line. It's the line of contact between the fluid body and where I'm measuring the force. All right. So if I thought about my system up here, then I could say that force of surface tension is balanced, if it's in equilibrium, by mg. And my force of surface tension is sigma times P, and I'll just write wetted, which equals mg, all right? And P wetted is what? Well, P wetted in this case, gamma, is the red line over here, which is 2 pi r, and equals mg. Well, what's mg? M is rho. What's the volume of this cylinder? It's 2 pi r times h, right? That's the volume, and then g. All right, so you can see in this case, it would be fun. I could figure out the density of the fluid I want to be able to hold up, or something to that effect, okay? Or we could just leave it in this and say, what is the mass I can hold up? Well, the mass is gamma over g times 2 pi r equals m, okay? Now, if the shape of the contact line were different, then it would be a different shape. Then I would use a different wetted contact line. So just for instance, what if I had said, instead of a circle, that red's going to be hard, I had a square. Now this would never happen. We'll talk about why later, because squares make bigger area. But if I had a square with sides a, then instead of 2 pi r, I would have had a squared, right? Or 4a, excuse me. All right, so that's the force. Now, another fun fact is we can think about what happens if I want to create more area. So let's say I take this system, I'm going to erase some of the stuff I've done, all right, and I keep it as a cylinder, all right, just erasing, lots of things to erase, lots of little dots and whatnot, all right. That's pretty good. All right, and let's say I do this as my initial shape, and then I pull on it with some force. So instead of mass, we're just going to say I pull on it with some force pull, such that it goes from this height, h, and I pull on it to make it go from h to a new height, 2h. And because of that hole in the top, there's plenty of water. I don't have to worry about that. All right, and as I pull it, it stays the same radius, r. And I might ask, what is the force? All right, how can I describe what 2h might be? All right, well, I might say that, if I thought about it from the force, that the force of surface tension is still equal to gamma times 2 pi r, all right? And that would have to be, if I did this in an equilibrium condition, right, equal to equal to my force pull, right? So force pull would equal force surface tension, and that would equal gamma times 2 pi r if everything was moving at the same time. Now, if I said how much energy did this take, I would say, well, the energy is equal to force times distance. In this case, it's gamma times 2 pi r h, all right? And that would be that. But there's another way I could think about it, which is to say, I know that the energy of surface tension is also is going to be equal to gamma times an area. And what's the area? Well, this is the area of new interface. Right? And so this could equal gamma. And what's my new interface in this problem? Well, it's 2 pi r, the circumference, times h. All right? And you can see I get the same answer. And the point of this is to say that the energy view and the force view of surface tension are identical. All right. What else happens? What else is surface tension important? All right, another interesting part about surface tension, the third important consequence, is the idea that it creates what's called a pressure jump across a curved interface. What does that mean? So let's draw a curved interface. All right, and let's say that this is a liquid bubble. I'm going to draw it in blue so we know better. Blue. All right, here's my liquid bubble, and it has a pressure on the inside, and there's a pressure on the outside. All right, And I've taken my bubble, and I've said, all right, I'm going to slice it there. And I'm going to say there must be some force of surface tension, okay, here. Now, maybe there is, maybe there isn't. We don't know yet. But let's assume, okay, that we know that there's some force balance in the y, and that this thing is in equilibrium, all right? Now, a couple of things we need to realize are that there's going to be some what we'll call A here, which is if I look down from the top-down view, all right, my little liquid bubble would look like a circle from the top, all right, and that is A, right? That's important because the normal force in the y direction is just going to be the pressure times that sort of cross-sectional area if we did a bunch of math, so don't worry about it. So if I said, okay, what's my sum of my forces in the y, all right? Well, it's Pi times that area minus P0 times that area minus the force of surface tension in the y. Now, why do I know there's a force of surface tension in the y? It's because I have this contact line here, right? This is, if I slice this off in the middle, there's a line there, all right? And so there's going to be a force of surface tension in the y around that contact line, all right? Now, that would mean that if I did a little bit of math, I would get what? Pi minus P0. If this is in equilibrium, this equals 0, right? Equals the force of surface tension in the y direction over that area. All right, now this is telling me that if force of surface tension is 0, Pi would equal P0, okay. But if force of surface tension is non-zero, then Pi does not equal P0. In fact, in this case, Pi is bigger than P0. All right, and we know that because there's a contact line there, there must be some force of surface tension. And so we know that for across a curved surface, Pi is not equal to P0. All right, this is called the Laplace pressure. All right, and in general, the formula is written like this, that pressure inside a curved surface minus the pressure outside a curved surface is equivalent to the surface tension, and this time I'm going to write sigma instead of gamma, all right, times 1 over R1 minus 1 over R2. What are R1 and R2? If I have an arbitrarily shaped surface like this, all right, and I draw a little dot where that's the center line, this little thing can have a curvature. If this is x and y, all right, it would have curvature R1 in this direction, and right, and then it might have a separate curvature R2. So any curved surface in 3D can be described by two radii. All right. So in general, that is the formula. All right. So for instance, if I have, let's just go up over. So for instance, if I have a sphere, let's just draw a little box here. If I have a sphere, then R1 equals R2. So the P inside minus P outside equals 2 sigma over R of the sphere. All right. And that's that. If I have, say, like a cylinder, all right, then this is R1, and R2 is infinite because it's a flat surface. And so Pi minus P0 is simply sigma over R1. All right, and so like I had a much more complicated shape, something that looked like this. Maybe right here, this is R1, and out here, this is R2. In this shape, then, the pressure 1 minus pressure 2 equals sigma, and the curvature R2 and R1, R1 is going to be positive because it's inside the surface, and R2 is going to be negative, so this would be 1 over R1 minus, and actually this is supposed to be plus down here, sorry, minus 1 over R2, all right? So I get this pressure jump across curved surfaces. All right, there's one more important thing that we need to know about surface tension, and that is that surface tension, all right, hold on, 4, so surface tension causes a contact angle at the three-phase contact line. All right. Now, what's a contact angle? Let's say I take a solid surface. I put a little drop of liquid on it here. So here's my liquid A. Out here I got air. All right. At this point right, oh, I wanted a different color. At this point right here, that's what we call the three-phase contact line. All right. And that's where air, water, and air, liquid, and solid are meeting. And if I zoom in on that little point, it would look something like this. All right. And there's an angle there. All right. This is called theta. And this is called the contact angle of a fluid. Now, if I thought about it in a very simple force equilibrium way and said, what's the sum of forces in the x direction? All right. You would say, now, what's interesting is we can talk about there being an interfacial tension or surface tension. We can also talk about it, remember, it's an energy, and we can have interfacial or surface energies between the liquid, the gas, and the air. All right. And so what we could do is say that sum of forces in the x direction is equivalent to 0 if it's in equilibrium, and that equals gamma of the liquid and the gas, in this case air, times the cosine of theta. All right, so there's essentially a force this way. All right, plus gamma of the solid and the liquid. All right, which is essentially to say that there is a force this way. And then minus gamma of the liquid gas, which is essentially there's a force this way. All right. Now, if we take all these formulas and we say they're in equilibrium, if we take this over here, we can solve for theta, and we get that the cosine of theta is equal to gamma solid air minus gamma solid liquid over gamma liquid air. All right. Now, you've probably heard of some of these terms before, but if theta is less than 90 degrees, all right, and remember theta is measured from inside the liquid, so it's from the solid surface to the liquid. This is a surface that we call hydrophilic, meaning water wants to be close to it. If theta is greater than 90 degrees, we say a surface is hydrophobic. And if theta is really big, so if we say theta is greater than like 130 degrees, we sometimes say it's super hydrophobic. All right. And that's the like stain defender pants that water beats up on and rolls off. And there are a lot of actually things in nature, lotus leaves, gecko paws, things like that, all right, that have super hydrophobic surfaces. In fact, I think the actual definition is 150 degrees. All right. So in fact, if I just come back over here, let me quickly erase some of the stuff on this slide. There we go. Okay. If we draw a little picture of it, it looks like this. You know, for a surface where theta is 0, you essentially get liquid spreading. If theta is somewhat less than 90 degrees, it forms a drop. If theta is bigger than 90 degrees, it forms a drop like this. And if theta is super hydrophobic, it looks like a bead of water on top of my system. And here, so this is theta of approximately 0, theta less than 90, theta greater than 90, and theta greater than 150. All right. The reason contact angle is typically important is if it directs the direction of surface tension forces. So if we just come back to our picture, if we think about a surface tension force here on the surface, then the contact angle tells us, right, the angle of the force, and so that lets us know the x and y directions. All right, so that is it for surface tension.